Hey guys, I'm just waiting for a few of you to come online if you do. If not, that's okay. I just wanted to let you know that I will be uploading lessons every day to a new YouTube channel, and I'll tell you about it towards the end. But right now I'm going to do some stuff for Algebra 1. Office hours will be Mondays 1 to 4 and Tuesday through Friday 9 to noon. 9 to 10 is for Algebra 1 specifically. 10 to 11 is pre-algebra, and then 11 to noon is open to anybody. I'm going to try and do little snippet lessons because there was one thing we didn't get to before all this started, so I want to go ahead and get that taught, or at least give you a resource to look at to kind of put things together. The new packet, it hasn't been printed at school yet, but if you have Google Classroom, it is uploaded into the class drive in your Google Classroom. So let's go ahead and get started. Today we're going to be working with basically finding square roots of stuff that aren't perfect squares and that have variables in them. So we're going to start dealing with radicals, mostly square roots and cube roots, but I'm going to show you some things that'll help you no matter what the root is. So right now I'm going to share with you my document camera so you can see what I'm writing on. All right. So what we're going to start with is when we are talking about roots, we are talking about the number, how many of a single factor goes with the same number. So this little number up here is called the index. The only time we actually see that is when it's something other than a square root. If it's a cubed root or a fourth root or a fifth root, that's when we'll see a number there. The little symbol thing right here, this thing that looks kind of like a division bar, is actually called a radical. And the number underneath it, the thing underneath the radical, is called the radicand. Okay. Now, the thing with, oh, hey, Daniel. The thing with square roots is if there's no index, you assume that it's a square root. Okay. Now, radicals that have more than one root happen because with square roots, it can either be positive or negative. But, it's most of the time we write down the principal or the main root or the positive root. We don't worry about the negatives quite so much.
I'm not leaving the fire.
Okay. Well, let me figure out what's going on, Daniel. I'm gonna have to stop sharing my screen. Hang on a second. There we go. Oh, and Lola. Hi, guys.
Where's my camera?
These are actually notes that are up in the class drive now, if y'all want to go look at them, but I'm just going to kind of go over them because this is what I didn't get to teach before we got out. So I'm going to go back to putting it on the notes. If we run across anything you don't understand, just let me know, okay? So, perfect squares. First perfect square you think of is the number 1 because it's 1 times 1, right? And then we have 4 and 9 and 16 and 25 and 36 and 49, 649, 8 times 8, 64, 81, 100, 121, and 144. So that's pretty much it. Now, so if I ask you to do the square root of 16, 16 we know is 4 times 4. So the square root of 16 is 4. We know that one. That's an easy one. We've been doing that forever. Okay. But what happens when we have a number outside the square root and a number inside the square root? Well, you treat this just as a multiplication problem. This is 6 times the square root of 189, and the square root of 189 is,
189?
sorry, 289
289, 17.
is 17. That's Mr. Barber in the background, by the way. He's also a math teacher. So this becomes 6 times 17, which is 6 and 7 is 42.
102.
102. Okay. So it's not too bad. Now, on your notes that are in the classroom drive, the directions for finding the square root are a little bit different than what's on my page. So I'm going to write them on a different sheet of paper. Okay. So what I do to find the square root, the first thing I do is I make a factor tree. Okay. Then I'm going to circle pairs of numbers. So pairs of matching factors. And then I'm going to write down one factor from each set outside the square root, and then leave stuff inside the square root. So what does that actually mean I'm doing? Okay, what does that mean I'm doing? What am I actually looking at here? So if I take the square root of 32, okay, 32 is 2 times 16, and 16 is 2 times 8, and 8 is 2 times 4, and 4 is 2 times 2. So now I'm looking for matching sets, pairs, because I'm doing a square root. So I have one set of 2's here, one set of 2's here. So that becomes 2 times 2 on the outside, and I had this one lone 2 left over, so it stays on the inside. So the square root of 32 is 4 times the square root of 2. Now, does it take a little bit longer? Yeah, but sometimes it's a whole lot easier than trying to figure out what the biggest square, perfect square is inside that. So like if I'm doing 180, 180 is 2 times 90, which is 2 times 45, which is 5 times 9, which is 3 times 3. So I have one set of 2's that comes out, and one set of 3's that comes out. And a 5 got left behind. You can kind of mark through these because we're breaking them apart. And we're just worried about the prime numbers on the outside. So the square root of 180 is 6 times the square root of 5. All right, so does that make sense so far? All right, awesome. So now, what do you think would happen if I added, I don't know, variables into it? Might make it a little bit different, but guess what? I'm not going to do that today. I'm just going to worry about finding square roots and cube roots today. I'll do variables tomorrow. So I want both of you to try, let me see, let me get, okay, I want both of you to try number 8. Try number 8. I'm going to do it in about a minute and a half, so y'all go ahead and try it. Y'all are having way too much fun playing with the screen. All right, so let's look at this. 175, because it ends in 5, I know it can be divided by 5. So that's 35. And 35 can be divided by 5, and you get 7. So these come out, and I get 5 times the square root of 7, and it's done. So that one wasn't too bad. Now, if we look at number 10, we're working with the same principle. We have to do the square root first and then put some stuff together. So if I'm taking the square root of 54, I've got to do 2 goes into 54 27 times, and 27 is 3 times 9, and 9 is 3 times 3. So this one set of 3's will come out. I already had a 2 here, times the 3 I took out, and I have a 2 and a 3 left behind. Didn't factor out. So now I'm going to do 2 times 3 is 6 times the square root of 6. So you just got to be patient with your factor trees, okay? Now, what happens if I change from doing a square root to doing a cube root? Well, cube root just means instead of looking for 2 things that match, I'm looking for 3 things that match. So perfect cubes are like 1 times 1 times 1, or 2 times 2 times 2, or 3 times 3 times 3. And I could keep on going if I wanted to, but you know, we need to look at other things. So how is doing the cube root different from doing the square root? The process is still the same. The first thing you want to do is you want to do that factor tree so you can see just the prime numbers and just those little factors that we can find groups of 3 in. Well, we know 8 is 2 times 4, and 4 is 2 times 2. So right there are my three 2's. So the cube root of 8 is 2. But what happens if it's not a nice number like 8 or 27 or 1,000? Well, what if it's negative? How does that change things? Well, the nice thing about a cube root is whatever's under the root decides whether your answer is positive or negative. Like on number 17, the cube root of negative 27 is the cube root of negative 3 times negative 3 times negative 3. So it's just negative 3. And that's something you have to be careful of with cube roots that you don't have to worry about with square roots, is that sign, that positive or that negative. We're still going to use the same idea though. We're still going to do our factor tree, but instead of looking for groups of 2 factors that are the same, we're going to look for groups of 3 factors that are the same. So with 40, 40 is 2 times 20, which is 2 times 10, which is 2 times 5. So right here along this outside edge, we have 1, 2, 3 2's that we can take out. So the cube root of 40 is equal to 2 times the cube root of 5. The cube root of 192. Start out by dividing by 2. That's 96. Divide by 2 again, that's 48. Divide by 2, that's 24. Divide by 2, that's 12. Divide by 2, that's 6. Divide by 2, that's 3. And the reason why I started out dividing by 2 is because it's an even number, and that's the easiest number to divide by when it's 2. Okay? So now I've got one group of 2's and another group of 2's. And this little 3 hanging out by itself. So when I go to do my answer, one group of 2's times another group of 2's times the lone 3 still left under the root. So my final answer is 4 times the cubed root of 3. Any questions yet, guys? Make sense so far? All right, so number 21. 2 times the cubed root of 432. Well, 432, I'm going to give myself more space over here. 432. Okay? It's even, so I can divide by 2. That's 216. Divide by 2 again. That's 108. Divide by 2. That's 54. Divide by 2, that's 27. Now, 27 is not an even number, so now I have to pick other numbers. Well, we happen to know that 27 is 3 times 9, and 9 is 3 times 3. So now let's look for groups of 3. Here's 3 2's right here. And here's 3 3's right here. So I have the 2 that's already there, times the 2 from this first grouping, times the 3 from the second grouping, but I still have this little 2 right here, and that gets left under the cubed root. So 2 times 2 is 4, times 3 is 12. So 12 times the cube root of 2 is my final answer. So no matter how complicated it looks, as long as we remember to break it down to our factors and do that factor tree, we're going to be able to do anything. If I had asked you to do a fourth root of this, instead of taking groups of 3, you would have taken groups of 4. Okay? So if we look at number 23, it's 8 times the square root of, times the cube root of negative 96. Looks like a nightmare, right? Break it down into its smaller pieces. Start with the negative 96. It's an even number, so it can be divided by 2. Okay, 2 goes into 96 48 times. And then that's 2 times 24. And that's 2 times 12, which is 2 times 6, which is 2 times 3. Now, I need some negatives in here, but I'll get to those in just a minute, okay? So here's one group of 2's. Make all those negative. Are there any more groups of 3-like terms? No, there's not. And I can make every single piece of this negative, because it needs to be a negative under my radical, and that's just the way it's going to end up. So now let's look. I have one group of negative 2. I already had 8. I have one group of negative 2, and what I have left behind is negative 2 times negative 2 times negative 3. So 8 times 2 is 16, so that's negative 16, times the cubed root. 2 times 2 is 4, times 3 is negative 12. So as weird as it feels, that's the way cubed roots work, Okay. All right, Daniel still got a thumbs up. Any questions on this, guys?
Okay, guys, I need to fix one thing. I did not realize until I was watching the video that I messed up, and so I'm going to fix it because I don't like messing up. So when we were doing number 23, and I factored everything out, all my 2's are going to be negative, but my 3 actually has to be positive. Because if you think about it, I have to have an odd number of pieces that have negatives for what's under the square root to be negative. And so when I finish this multiplying out, it becomes negative 16 times the cubed root of 12 instead of the cubed root of negative 12. And that's just something you've got to be careful of. All the factors that are the same will have that negative, and the factor that's different will not have that negative. So that's something you have to watch for. Okay. Good luck, and I'll see you all again tomorrow.